Perovskites are a fascinating class of materials with a unique structure. Imagine a cube-like framework of atoms. This structure allows for a wide range of chemical compositions. Cocoa perovskites are a specific type where cobalt and copper atoms occupy key positions within this framework. Now let's introduce alkali metals like potassium or rubidium. These alkali metals don't simply replace the existing atoms. Instead, they nestle themselves within the perovskite lattice. Think of them as strategically placed guests in the perovskite framework. This strategic placement has profound effects on the catalyst properties and performance. These alkali metals hold the key to unlocking the true potential of cocoa perovskites in higher alcohol synthesis. The introduction of alkali metals brings about significant changes in the cocoa perovskite catalyst. One crucial change is the increase in surface area. The alkali metals create tiny pores and channels within the catalyst. This increased surface area provides more space for the reactants to interact, but that's not all. Alkali metals also influence the arrangement of atoms within the perovskite structure. This altered arrangement can create more active sites on the catalyst surface. These active sites are where the magic happens. Finally, alkali metals can even change how electrons are distributed within the catalyst. This change in electronic structure can further enhance the catalyst's activity and selectivity. Imagine a chemical reaction where simple molecules like carbon monoxide and hydrogen, collectively known as syngas, transform into valuable higher alcohols. This transformation is precisely what cocoa perovskite catalysts facilitate. Under high pressure, these catalysts act as matchmakers. They bring carbon monoxide and hydrogen molecules together in just the right orientation. This interaction breaks the bonds in carbon monoxide and hydrogen, allowing new bonds to form. The result, a mixture of higher alcohols, primarily ethanol, propanol, and butanol, emerge from this molecular dance. Section 4. The alkali advantage, boosting reaction rates and selectivity. The addition of alkali metals takes this catalytic process to another level. Alkali ions, like potassium or rubidium, act as promoters. They enhance the catalyst's ability to accelerate the reaction rate. This means more syngas is converted into higher alcohols in a shorter amount of time, but there's more. Alkali promoters are not just about speed, they're also about precision. They can suppress the formation of unwanted byproducts, particularly methane. Methane is a less desirable product in this process. Alkali metals steer the reaction pathway, favoring the production of valuable higher alcohols over methane. Section 5. Potassium and rubidium star players in alcohol synthesis. Among the alkali metals, potassium and rubidium stand out as exceptional promoters for cocoa perovskite catalysts. Potassium, with its optimal size, fits snugly within the perovskite structure. This perfect fit enhances the interaction between the catalyst and the reactants. Rubidium, on the other hand, with its slightly larger size, introduces subtle distortions in the perovskite framework. These distortions create even more active sites, further boosting the catalyst's activity. Both potassium and rubidium showcase the remarkable ability of alkali